How subsurface conditions influence building design. Welcome to Blueprint to Reality, your hub for exploring civil and structural engineering concepts in depth. In today's episode, we're diving into the crucial topic, how subsurface conditions influence building design. This often overlooked aspect plays a fundamental role in ensuring the safety and durability of any structure. Let's uncover the secrets hidden beneath the surface. The importance of subsurface conditions in construction. Every building, from a modest house to a towering skyscraper, depends on a solid foundation. Subsurface conditions refer to the physical properties of the soil and rock layers beneath the surface. These properties dictate how much load the ground can support, how it will react to moisture, and how it behaves under pressure. If these conditions aren't properly assessed, even the most meticulously designed structures can face issues like uneven settlement leading to cracks, structural instability due to shifting soil, water intrusion that weakens the foundation. Key factors in subsurface conditions. 1. Soil composition. Soils are incredibly diverse and behave differently under load. For instance, clay soils expand and contract with moisture, which can lead to uneven settlement. Sandy soils offer good drainage but may shift under heavy loads. Silty soils are prone to erosion and can destabilize foundations over time. Understanding soil composition helps engineers determine whether the ground can naturally support the structure or if it requires improvement. 2. Bedrock and load distribution. Presence of bedrock. When bedrock is close to the surface, it provides a stable base for heavy structures, minimizing the need for extensive foundation work. Deep bedrock requires costly solutions like piling or caisson foundations to transfer the building's load to a stable layer. 3. Water table and groundwater conditions. High water table can lead to hydrostatic pressure, causing water to seep into the structure and weaken it over time. Drainage challenges. Poor drainage in areas with a high water table necessitates advanced waterproofing and drainage solutions to protect the building's integrity. Engineering solutions for subsurface challenges. 1. Soil testing and analysis. Geotechnical engineers conduct detailed soil tests before construction begins. These tests measure properties like bearing capacity, how much load the soil can support; compressibility, how much the soil compresses under pressure; shear strength, the soil's ability to resist sliding forces. 2. Foundation design. Based on subsurface conditions, engineers choose appropriate foundation types. Shallow foundations, suitable for stable soil near the surface. Deep foundations, used in areas with poor surface soil, transferring loads to deeper, more stable layers. 3. Improving soil conditions. In cases where soil isn't naturally suitable, engineers use techniques like compaction, compressing soil to increase its density; grouting, injecting materials into the soil to improve strength; reinforcement, adding geosynthetics to stabilize weak soils. 4. Drainage and waterproofing systems. For areas with high groundwater, solutions include installing sump pumps to remove excess water, using waterproof membranes to protect the foundation, designing drainage systems to channel water away from the building. Real-world examples of subsurface challenges. 1. The Leaning Tower of Pisa. This iconic structure tilted because the clay beneath it couldn't evenly support its weight. It's a classic example of why thorough site investigations are essential. 2. The Burj Khalifa. The world's tallest building in Dubai stands firm due to its robust foundation design, supported by detailed subsurface investigations and advanced piling techniques. Conclusion. Subsurface conditions are the hidden forces shaping every building's destiny. By understanding and addressing these factors, engineers ensure that structures are safe, durable, and resilient. Thorough subsurface investigations form the cornerstone of sound engineering, saving time, costs, and lives in the long run. Thank you for tuning in to Blueprint to Reality. Don't forget to like, share, and subscribe for more in-depth explorations of civil and structural engineering concepts. See you in the next episode. Geotechnical testing methods explained. Welcome to Blueprint to Reality, your hub for exploring civil and structural engineering concepts in depth. Today, we're diving into geotechnical testing methods explained, where we uncover how engineers assess soil and rock properties to ensure safe and reliable construction. These methods form the foundation of every project, helping to identify challenges before they arise. What are geotechnical tests? Geotechnical tests are scientific methods used to evaluate the properties of soil and rock beneath a construction site. These tests provide essential data for designing foundations, retaining walls, and other structural elements. Without proper geotechnical testing, structures risk failure due to unforeseen soil conditions. Why are geotechnical tests important? Foundation safety. Ensure the ground can support the structure's weight. Prevent failures. Identify and mitigate risks like settlement or soil movement. Cost optimization. Avoid over-designing foundations by accurately assessing soil properties. Key geotechnical testing methods. 1. Field tests. Field tests are conducted directly on-site to analyze in-situ soil conditions. Common methods include Standard Penetration Test, SPT. This measures soil resistance by driving a split-barrel sampler into the ground. The number of blows needed to penetrate a certain depth indicates soil density and strength. Cone Penetration Test, CPT. A cone-shaped probe is pushed into the soil to measure resistance. CPT provides continuous data on soil stratigraphy and load-bearing capacity. Plate Load Test. Engineers place a steel plate on the ground and apply incremental loads to assess soil-bearing capacity and settlement characteristics. 2. Laboratory tests. Laboratory tests analyze soil and rock samples under controlled conditions. Key methods include Grain size analysis. Determines the proportions of sand, silt, and clay in a soil sample. This helps classify soil types and predict behavior under load. Atterberg limits test. Measures the plasticity of soil, indicating how it reacts to changes in moisture content. This is critical for understanding expansive soils like clay. Triaxial shear test. Assesses soil strength by subjecting samples to controlled stress conditions. This data is crucial for designing retaining walls and slopes. 3. Geophysical methods. These non-invasive techniques use waves and vibrations to study subsurface properties. Examples include Seismic refraction. Measures the speed of seismic waves through the soil to determine layer stiffness and density. Ground penetrating radar, GPR, uses electromagnetic waves to create a subsurface map, identifying features like voids or buried utilities. How engineers use geotechnical test data. The data from these tests guides critical decisions. Foundation design determines whether shallow or deep foundations are needed. Slope stability analysis identifies risks in hilly terrains. Earthwork planning ensures proper compaction and grading during construction. Real-world example. One of the largest projects to utilize comprehensive geotechnical testing was the Channel Tunnel between the UK and France. Engineers conducted extensive soil and rock tests to ensure the tunnel's stability beneath the seabed. This meticulous testing prevented collapse and ensured long-term safety. Conclusion. Geotechnical testing is the unsung hero of modern construction. These methods provide the critical insights engineers need to design safe and efficient structures. Without them, the risks of foundation failure and structural instability would skyrocket. Thank you for joining us on Blueprint to Reality. Don't forget to like, share, and subscribe for more fascinating insights into civil and structural engineering. Stay curious, and see you in the next episode.